Swayam Prabha. Digital India. Educated India.
Hello and good morning. We continue with B-spline segments and curves. This is lecture number 31. Over the last 10 or so lectures, we have learned a great deal about B-spline segments and curves, how to design B-spline basis functions, and how to use them to further design B-spline curves. Today, we will be working on coding to understand how B-spline basis functions, segments and curves, and essentially related concepts can be implemented. Let's revisit normalized basis splines. A normalized basis spline of order 1 is given by n1 sub I, where ti is the last knot over which n1i would stand. This is a function of parameter value t, and this is equal to delta sub I, such that delta sub I is equal to 1 for parameter value t belonging to the interval ti minus 1 ti. The left hand side is closed, the right hand side is open. Otherwise, n1i of t is 0 elsewhere. In general, the recursion formula is given by nki of t equals t minus ti minus k over ti minus 1 minus ti minus k times nk minus 1 I minus 1 of t plus ti minus t over ti minus ti minus k plus 1 times nk minus 1 I of t. The first goal for us would be to write a function to determine any B-spline basis function of order k, of which the last knot is t sub I. You can use any mode to perform your coding. I'm comfortable with MATLAB, so I'm going to be demonstrating the implementation using that software. So I'm going to be writing the function to determine B-spline basis function. Function some value is equal to, let me call this function nb underscore spline basis, and we'll be passing some parameters into this function. Let me pass a few parameters, say m, I, capital T and small t. M would be the order of the B-spline basis function. I is the index, I'm writing this thing in capital letters, index of the last knot over which this spline function stands. So I'm just going to copy and paste. Capital T is the knot vector and small t is the parameter value at which this spline function is to be computed. Let's start with the coding. We have a few cases. Case 1 is when m is equal to 1, and then case 2 is when m is greater than 1. Let's write the codes for these two cases. If m is equal to 1, then something else. This would be the case where m is greater than 1, and then we'll have some arguments. We'll finally end this if statement. Here I'm going to be nesting another if statement. If the parameter value t is smaller than, rather is greater than or equal to t I minus 1, and if t is smaller than ti, then value should be equal to 1, else value should be equal to 0. End. This is where we compute order 1 basis spline functions. So clearly the parameter value t has to lie in between the not span capital Ti minus 1 and capital Ti. Next, consider the case where m is greater than 1. We explicitly impose this case. If m is greater than 1, we end this if statement. We are going to be using some arguments in between here. So essentially here I'm going to be computing nki, which has 4 components. This coefficient, the basis function of 1 order less, and then this coefficient, and again a basis function of 1 order less, with the last not as I. Let me call these two coefficients small p and small q. So I'm going to say p is equal to, I'm just commenting as of now, small t minus capital T I minus m over T I minus 1 minus capital T I minus m. Likewise, another coefficient q is equal to, I just copy and paste this. Here I'll have T I minus T. I won't need this. And in the denominator, I'll have Ti minus Ti minus m plus 1. So once we have the expressions for the individual weights which are linear, p and q, let me code them now. So we first compute p, and then we compute q. Let's go back to this expression. This is the coefficient p that we are interested in computing. This is q that we would want to compute. Now notice that in case we are working with multiple knots, Ti minus 1 can be equal to Ti minus k. Likewise, Ti can be equal to Ti minus k plus 1. We'll have to take care of these conditions explicitly. Let's work with those conditions. If Ti minus 1 is not equal to Ti minus m, then I should be able to compute p as this expression here. Else, and then end. What should p be in this case? We'll come to that a little later. Likewise, I just copy this and paste it here. I'll copy the expression for q and paste it here. This is the equal to sign and this is q. Here I need to ensure that Ti is not equal to Ti minus m plus 1. So in case we are not considering multiple knots here, q will have this expression, capital Ti minus t over capital Ti minus t of I minus m plus 1. In case these conditions are satisfied, we have the expressions for p and q like so. In case of multiple knots, what would the value of p and q be? Let's work this thing out on the board. So we have the knots Ti minus k plus 1, Ti minus k plus 2, and so on, up till Ti minus 1 and Ti. In the recursion relation, we have two basis splines, each of order k minus 1, one of which is standing with the last knot as Ti minus 1, and the other one is standing with the last knot as Ti. With n k minus 1 I minus 1 of t, coefficient p is associated, and with n k minus 1 I of t, coefficient q is affiliated. Now, the condition that Ti minus k will be equal to Ti minus 1 will be only physically possible if all the intermediate knots, including Ti minus k and Ti minus 1, are multiple knots. So we'll have two cases here. Case 1, that t is equal to this knot value, which will be equal, or t is greater than Ti minus 1 or smaller than Ti minus k. In case of multiple knots, when Ti minus k plus 1, and so on up till Ti minus 1 are all equal, and in case t is equal to this knot value, if you look at the expression for p, p will be taking the 0 over 0 form. By convention, we assume that this is 0. For all the other values of t, nk minus 1, I minus 1 of t will be 0. Likewise, if we have these multiple knots where Ti minus k plus 1, Ti minus k plus 2, Ti minus k plus 3 are all equal to Ti, again we'll have two cases. Case 1, when t is equal to all these knot values, in which case again the expression for q will assume the 0 over 0 form, which by convention we treat as 0. Otherwise, for t not equal to these multiple knots, n k minus 1 I will be 0. We'll keep this in mind and use p equals 0 here and q equals 0 here. If you look at this expression here, we have computed p and q. We are yet to incorporate this recursion relation. So we'll go back here and we'll say that the recursion relation is to be incorporated here, and we'll set the value VAL equals p times. Now here is the trick. I can use the concept of function within a function. In a sense, I can use this same function to compute B-splines of order 1 less, 2 less, and so on. Once we understand this, I'll say NB underscore spline underscore basis. Here we have order m minus 1. Here the last knot over which this spline is standing is I minus 1, the knot vector t, and the parameter value, plus q times NB underscore spline underscore basis. Once again, order 1 less, last knot here is ti, the knot vector capital T, and the parameter value. This should be adequate for us to compute a B-spline basis function of order m with the last knot as t sub I. I'll save this file as in B-spline basis. It's time now to test this file. For that, I'm going to be using a new function. I'm going to be using some commands which are typical for MATLAB. Clear screen, figure 1, clear access, clear all variables. Let's test the previous function NB spline basis for order 4 splines, and let's test for a very general knot vector with 10 knot spans or 11 knots. Let me comment here. Order is given by m, t is the knot vector, which is uniform in our case. We'll talk about knot vector generation in a little while. Now let's plot a few B-spline basis functions. For index I, 1 to let's say 200, let's generate a parameter value t. This is equal to index I minus 1 over 199. I'm using t equals I minus 1 over 199 so that I can generate the value of t between 0 and 1. If you see, for I equals 1, t is 0, and for I equals 200, t is 1. Let me first end this for loop and continue further. At this time, let me not worry about the full support, and let me allow my parameter values to go from 0 to 10. Let me store these parameter values in a vector x of I. This is 1 minus t, which is this variable here, times t 0, which is this value here, plus t times t 11, which is this value here. And now it's time for us to compute the B-spline basis functions. Let me write them in short. BSBF, standing for B-spline basis functions. How many of these B-spline basis functions will be possible? You know that already from the previous lecture. It would be 7 of them. So the first one will be given by NB spline basis. The order is M. We'll have the last knot mentioned in a little while. The knot vector is capital T and the parameter value is small t. Let me be a little careful here. The first of the B-spline basis functions will be standing over 4 knot spans. This is the first knot span, the second knot span, the third knot span, and the fourth knot span. This would be the last knot over which the first B-spline basis function will be standing. The index for that knot corresponds to 5. Since m is equal to 4, I can write the index here as m plus 1. Is it okay for me to use small t for the parameter value here? If you realize, I'm storing the parameter value in this array x of I. So I can replace this small t by x of I. All I need to do is now copy and paste this statement a few times. Since we have 7 B-spline basis functions, I rename the variables on the left hand side accordingly. The order would remain the same. The knot vector t will remain the same. The parameter values will remain the same. Just that the last knot over which the respective B-spline basis functions are standing will change. This would be m plus 2, m plus 3, m plus 4, m plus 5, m plus 6, m plus 7. I have already ended the for loop. Let me now select all text and make the code look a little beautiful. Let's now plot the B-spline basis functions. MATLAB has the command plot for that. Plot x BSBF 1. Let me plot the first one using the red color R, and let me specify the line width as 3. I can use the same command to plot all the other functions. This is the second B-spline function, third, fourth, fifth, sixth, and seventh. Let me choose different colors to plot them. This one is, let's say, green. This one is, let's say, blue. This one is magenta, cyan, black, and yellow. Let me also specify the line style, which is solid in all cases. We are now ready to see the plots of these 7 B-spline basis functions. I'll save the file as NB spline basis test. Let me execute this file and see how the plots may look like and whether I may have committed any mistake in coding. Looks like I have. Apparently, I have made a mistake in the coding here. MATLAB does not allow the indices to be 0 or negative. Maybe I should have chosen T1 in place of T0. Let me go back and execute the code again. Now I see only one of these B-spline basis functions. What I have done is I have not used the option hold on. Let me use this. Let me save this file again and execute the code. Now we see all the B-spline basis functions. Let me change the figure properties a little bit. Set the background as white and set the font size as, let's say, 20. Now this is a lot better now. Can you name this B-spline basis function? As per our convention, this would be N4, 4. This is N4, 5, N4, 6, N4, 7, N4, 8, N4, 9, and N4, 10. So far, we have been coding the B-spline basis functions, and we have just tested them. Let's play a little more. Let's go back to our editor and start modifying these nuts. In a sense, let's introduce multiple nuts and see what happens. Let me increase the multiplicity of the second nut by 1 or maybe by 2, so that the second nut is now having multiplicity 3. What changes do we expect? The B-spline basis functions, they change in shape locally. Now if you realize, at this nut value 1, the first B-spline basis function has the value 1, and all the others have the value 0. This concurs with the local barycentric property. Let's go back to our editor and even make the first nut as 1. Do we see any change? Let's find out. We do not see much change except for the fact that this part of the first B-spline basis function is now absent. How about if I increase the multiplicity of this nut by 2, making T8 here a nut of multiplicity 3? So I change this value to 7 and this value as well to 7. I execute this code again. Now we have the last basis function with value 1 as the parameter value 7. All the other B-spline basis functions at this not value are 0. We go ahead and change the last not value to 7 to see what happens. Not much change, just that the last not value is now 7. The last basis function still has the value 1, and all the other previous basis functions have the value 0 at t equals 7. Let's go back to our editor. Modify these knots to what they were before. And increase the multiplicity of any intermediate knot. Let's say I make these 3 knots have the value 4. Do I expect any change? Yes. B-spline basis functions which are associated with this not value change locally in shape. You can experiment in whatever way you feel like to be comfortable with the concept. So we are just about done testing the normalized basis spline function, for which we constructed a test function here. We also experimented with multiple knots. We had the first knot as a multiple knot of multiplicity 4, which was the order of the B-spline curve or the basis function. Likewise, we also tested for the last knot having multiplicity 4, and for any other intermediate knot, we tested for its multiplicity. We are now ready to design B-spline curves. For that, we would need to introduce data points. Let's start with a new function. Some typical MATLAB commands. Clear all variables, clear screen, the first figure, and here let me comment that we are designing B-spline curves. Let me work with 2-dimensional data points for now. I'm storing the x and y coordinates in an array P. Let me arbitrarily specify these data points. I have arbitrarily specified the x and y coordinates in array P. Let me copy this to the workspace of MATLAB So this is how my array P looks like. Let me compute the number of design points. These are n plus 1 of them. N is equal to the size of P minus 1. Going back to the workspace, size of P indicates the number of rows and the number of columns. Here we have 8 rows, 1, 2, 3, 4, 5, 6, 7, 8, and we have 2 columns, 1 and 2. So if we say that the number of design points are n plus 1, n would be the number of rows in P minus 1. Let me specify the order. Let me denote the order by P, and let me say for now that P is equal to 5. We are working with order 5 B-spline curves. The number of knots will be m plus 1, where m is equal to n plus p. We get the value of n from here, and we have just specified the order p. For now, let me specify arbitrarily a knot vector. For this case, I would already know what m is. This is 7 plus 5, 12. So the number of knots will be 12 plus 1, 13. Accordingly, I specify capital T as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Alternatively, I can also specify T using the for loop. For I going from 1 to m plus 1, T of I is equal to I minus 1. We'll worry about clamping this B-spline curve later. Let me just comment it as of now. Let's now worry about the interval of full support. And this would be given by the interval a, b. Now, what is a and what is b? Let me copy this piece of the code to the workspace, and let me see what T is for us. It's a set of integer values from 0 to 10. Let me double check what m is. So it looks like we have been working with order 4 B-spline curves. So the workspace contains the value or the values of previous variables. Let me go back to the editor, save it as B spline curve test. This command here is going to wipe out the values of all the previous variables. Let me execute the code to that effect. Let me not worry about this error for now. I was able to resolve the error. Now I am back with the values of the not vector. So the transpose of the not vector is given by this column from 0 to 12. In all, 13 nuts. Now we are working with order 5 B-spline curves, and we are looking for the knot values that form the full support for the B-spline curve. For that, we need to count the first 5 knot spans. This is 1, 2, 3, 4, and 5. And looks like this knot will be the knot that will be defining the lower bound of the full support. T0, T1, T2, T3, T4. So A here should be T P. Now, if the index starts from 0, then this value should have been P minus 1. But since in MATLAB the index is starting from 1, even though the value is 0, this index here will correspond to P. Let me uncomment the statement. How about the rightmost value of the interval? We revisit the knot vector again and start counting the knot spans from the bottom. First knot span, second, third, fourth, and fifth. Looks like this value here, T9, would correspond to B. What is T9 for us? This is T M plus 1, the number of knots, minus P minus 1. Let me uncomment this too. Let me copy these statements to the workspace and verify if you're correct. So A has the value 4 and B has the value 8. So we are okay, in fact. Let us continue and generate a B spline curve. Let's also plot the corresponding Bezier curve to compare the two curve models. We'll worry about Bezier curves in a little while. Now let's say we have about 150 points. So we raise our index I from 1 to 150. Let's have a parameter value T1 between 0 and 1, for which we compute T1 as I minus 1 over 149. Clearly, for I equals 1, T1 is 0. For I equals 150, T1 is 1. Now let's have a parameter value T vary between the two values A and B. For that, we'll have 1 minus T times A plus T1 times B. This should actually be T1. Before I mess up the code, let me end this for statement and continue further. Now let's store the x and y coordinates of the curve in two arrays, xi. We initialize this thing to 0, and yi for the y coordinates. We initialize this also as 0. Now these are the x and y coordinates of the spline curve. So we mention this. Likewise, we store the x and y coordinates of the Bezier curve as well. We store them in two arrays, bex I and bey I. We set both to 0. I would want you at this time to recall the definition of B-spline curves. That is a weighted linear combination of B-spline basis functions and the corresponding design points. Let me run a nested for loop to compute the two curve models. For k equals 1 to n plus 1, if you remember, n plus 1 is the number of design points. I end this for loop here, and within this for loop, I compute the two curve models. For B-spline curve, I have x of I equals x of I plus NB spline basis. Remember the construction. Let's look at the variable value we had chosen to specify the order, and that is P. We come back here, we specify the order of the B-spline basis functions. We specify the last knot, we specify the knot vector, and we specify the parameter value. The parameter value T is going from A to B. This is our range of full support for the B-spline curve. Remember that T is not normalized to have the values between 0 and 1. It is T1 that has the values between 0 and 1. So we have just computed the x coordinates of the B-spline curve, but not yet. I need to multiply by capital P K 1 the x coordinates of all the data points. Likewise, I compute the y coordinates. For that, I copy and paste, go back and change this statement slightly. These are y's. The B-spline basis functions will remain the same, just that the data points here will now have the y or the ordinate information. Let me expand this window a little bit. How about the Bezier curve? I would here want you to recall the construction of Bezier segments. I'm going to be using a coefficient c, which I'll be computing as factorial something over factorial something times factorial something. Now this number here within the parenthesis should be the number of data points. Should it be the number of data points? Or rather, should it be the number of data points minus 1? So we have the number of data points as n plus 1 minus 1, which would make it n. Within the parenthesis here, I should be actually computing the factorial k minus 1. Why k minus 1? Because my index k here is starting from 1, while the relation that we had developed for Bezier segments had the index k starting from 0. So I need to make that little adjustment. Here will be n minus k minus 1. Let's see if this expression is a valid expression. Let's arbitrarily take the value n equals 6, k equals 3. Copy the statement and get the value of c. So it looks like a valid construction. We move further and we say c equals c times 1 minus t1 raised to k minus 1 times t1 raised to n minus k minus 1. Now this variable c will have the value from this statement. These are the other expressions pertaining to the Bernstein polynomials. And of course, my parameter value here will be going from 0 to 1. Let's continue further. We say Bex of I is equal to Bex of I plus the Bernstein polynomial, which will be stored in C, times the x coordinate of the kth design point. Likewise, we'll have a very similar expression for the y coordinate. and this would have values of the ordinates on the design points. Looks like I'm just about done coding for Bezier curves and B-spline curves. All I would need now is to write some statements to plot them. Plotting the B-spline curve. B-spline curve has information stored in the x and y arrays. So we'll have plot x, y with color red and line style solid, line width as 2. We would further want to keep continuing plotting different data. So we'll use the command hold on. We'll also plot the design points. The first column of the design points are given by P within parenthesis colon comma 1, and the ordinate values of the design points are stored in the second column, for which this value is 2. Let me use magenta star to mark these data points, and let me use a slightly larger marker size of, let's say, 16. I've already used this command hold on here. I'll not be needing it anymore. Now let me plot the Bezier curve. All I need to do is copy the statement, paste the statement here, and replace the x and y arrays by the BEX and BEY arrays. Let me use a different color to plot the Bezier curve. The color I'm using is blue. Let me also go ahead and plot the control polyline. Just to help us retain the perspective. I'm going to be using the for loop for this. And I'm going to be using the line command. So this expression here will have information about the x coordinates of 2 consecutive points in a polyline, pi1, pi plus 1, 1, and likewise the array here will have the information pertaining to the ordinates of the design points. So I'll change the column value here. I'll use the black color. I'll use the line width as, say, 3. And the line style as, maybe, say, dashed. and I have to end this for loop, which I'll do right away. So it looks like I'm done writing the code for plotting B-spline curves and segments. Let's see if the code works. I may or may not have made errors in writing the code. Let's execute this file. I get the result in a single shot. This is interesting. Let me change the figure properties here. Let me increase the font size of the numbers. So the star points in magenta represent the design points that the user has specified. The dashed line represents the control polyline. The curve in red shows the B-spline curve, and that in blue shows the Bezier curve. Now this is a curve of order 5, as you would know, and it's up to you to figure out what the order or the degree of this Bezier curve is. Notice that the B-spline curve is plotted for values of t, the parameter, in the full support range. We are just about done writing a code to generate B-spline curves. Let's experiment further with that code. Specifically, let's experiment with the end conditions and data points. We can think of clamping the first end of the B-spline curve, clamping the last end of the curve, or maybe clamping both the ends. We can also think of moving data points or adding data points. Since we already have written the code to generate a corresponding Bezier curve, we will be comparing our B-spline curve side by side with the corresponding Bezier segment. So let's continue with the coding. So if you recall, I had left some space for clamping conditions. Let me use that space now. So here, let me first think of clamping the first end. For that, I'm going to be increasing the multiplicity of the first knot by p, the order. So I'll say for I equals 1 to p, ti is equal to tp, end. Let me also write the clamping condition for the last point. Clamping the last end. Here, a similar piece of code can be used, but with slightly different logic. Here, we are going to be making the last knot a multiple knot of multiplicity p. How many knots do we have? We have m plus 1 of them. So we'll have to figure the entries in these parentheses appropriately. So this entry here will be m plus 1 minus p minus 1. Rather, this would be I minus 1. This entry here will be m plus 1 minus p minus 1. Let's go forward and see what this value is. This value is the one that this variable b carries, the last knot of full support. And all the other knots on the right of this will have the same value as this. Therefore, this index here. Let me comment this piece of code for now and generate my B-spline curve with only the first end clamped. Observe the red curve. It passes through the first data point. Let me go back to my editor and uncomment this piece and execute the code again. What has happened? Why do we get this singularity? If you recall, I have always been referring to intervals such that the interval is closed on the left and is open on the right. Maybe it has to do something with that. I would like you to think about this as an exercise. Let me go back to my editor and go back to where I'm using the parameter values to generate my B-spline curves. Maybe it is here. What I would do is I would subtract a very small value from t. This is quite small for our purpose. Let me execute the code now after making this modification. Now I get a much better looking B-spline curve, which passes or tends to pass, or at least gives the impression that passes through the last data point. Let's now experiment with the position of these data points. Let's go up and arbitrarily change different values here. Let this be 7. Let this be 18. Let me now clear the axis of this figure so that we can compare the new results. So the information in figure 1 stays, and let me plot the two curve models using different colors. Let me use green for the B-spline curve and maybe magenta for the corresponding Bezier curve. Let me plot the new control polyline using color yellow. Let me go up and change the entries further. Let me make this 11, make this -8. Let me work with 2 here, make this 8. and execute the code now. The red curve here is the original B-spline curve. This blue is the original Bezier curve. The green one here is the new B-spline curve. And the magenta here is the new Bezier curve. Look at how closely the B-spline curves follow the undulations reflected by the control points, or the control polyline for that matter. Why do you think this is possible? It is because of the strong convex hull property, or the strong local barycentricity that the B-spline basis functions have to offer. Let me add a few more points as the last experiment for this lecture. I add 0.156, 17, 2. Let me go back a little bit. 10, 8, 8, 20, and maybe 9, 22. I'm arbitrarily specifying these data points. Let's now see what happens. Looks like I have made an error here. I shouldn't be using the semicolon. Okay, let's see what happens now. Try to concentrate on this green curve here. And this magenta curve here. Now, if you notice, a part of the B-spline curve remains the same, only some part changes in shape. Again, emphasizing local shape control. Whereas this new Bezier curve changes globally in shape. It may be fun and it may be a lot easier for you if you learn the concepts properly to play or experiment with B-spline curves. You can think about how you can interactively move these data points, how you can automate the knot vector generation. We haven't talked about that, but you can think of computing the knot vectors like the way we discussed in the previous lecture. You may want to write another function to generate this array.